SwayamPrabha. Digital India. Educated India.
Welcome back. So, we will continue with the lecture 4 for the course Combustion of Solid Fuels and Propellants. So, we will resume from where we left with in the previous lecture. So, we are discussing about the various performance parameters of rocket. So, if you recall, we had derived one equation for characteristic velocity or C star. And we denoted the C star characteristic velocity as C star, and we got the equation of C star something like square root of RTC by capital gamma, where R is the gas constant for that particular gas, which is going to be universal gas constant divided by the molecular weight, and the capital gamma we got as a function of small gamma or the specific heat ratio, which is square root of gamma into 2 plus gamma 2 by gamma plus 1 to the power gamma plus 1 by 2 into gamma minus 1. So, this was the equation we already got, and if we recall that we can relate the mass flow rate, chamber pressure and throat area by the relation C star equal to P C A T by m dot, where P C is the chamber pressure, A T is the throat area, m dot is the mass flow rate. Now, let us try to understand what exactly C star is telling us, or what is the indication given by the C star. C star is basically a function of the propellant characteristics and the combustion chamber design. It is not dependent on the nozzle characteristics, that we can say. In other words, we can say that C star is a index of performance of the propellant and the combustion chamber design. So, it can tell us like how a particular propellant has the capacity to generate high temperature gas and to raise the chamber pressure. So, that is somehow we can say it is an index of performance. So, overall we can say that the C star or the characteristic velocity can be considered as a figure of merit or index of performance for comparison of various propellant combinations and combustion chamber design. Now, one can obtain the ideal value of C star or C star ideal, which is you can say it is like maximum value of C star from the the ideal gas assumptions, like ideal gas assumptions we had, or we had followed like the perfect gas assumptions. So, from there we need to find out the value of the ideal value of chamber pressure, mass flow rate and the throat area. From there we can get the ideal characteristic velocity. Now, of course, the actual characteristic velocity may not be the equal to the C star ideal. So, there is a parameter defined, it is called the eta C star or C star efficiency, which is defined as the C star actual by the C star ideal. Now, how do I find out the C star actual or the actual characteristic velocity? We can find out the C star actual from the experimental data, like if we get the P C value or the chamber pressure or the m dot and A T from experiment, we can actually fit this value in the C star equation. So, now our C star actual will be equal to P C A T by m dot of course, for actual cases, means we need to find out the values from the experiment. In many occasions, chamber pressure is derived from the chamber pressure is obtained from the pressure transducer data we install during the test. So, one can see that there may be some pressure transducer installed which can tell us the chamber pressure or the value of chamber pressure, the actual chamber pressure, and we can feed this data. M dot can also be calculated from various measuring technique, like if we know the regression rate of the solid propellant, from there we can estimate the m dot value, and AT we know, which is the throat area. So, for actual cases, if we know the values of PC, AT and m dot, we can find out the values of C star actual, and from the ideal gas assumptions or perfect gas law, from there we can actually find out the C star ideal by considering the ideal value of PC, m dot and AT. So, of course, our objective is to make this C star actual as close to C star ideal. So, in a typical range, if you say typical range of C star is around 0.92 to 9.995, means 92% to 99.5%. So, it is quite high value, the efficiency, C star efficiency is quite high value. So, our aim is to make it like as close to the ideal case. So, that is the value of C star efficiency. The other parameter is another important concern is the thrust coefficient. Is CF, denoted as CF. In order to understand the thrust coefficient, we have to recall the thrust equation we had in our previous discussions, like thrust equation was F equal to m dot into Vj plus P minus Pa by Ae, where we already said that Vj is the jet velocity or the efflux velocity, P is the exit area, P is the pressure at the exit of the nozzle, Pa is the ambient pressure, A is the exit area, m dot is the mass flow rate. Now, if we look at this equation, what the principle of thrust generation? Thrust generation is the principle by which the efflux of propellant is taking place, or efflux of propellant gas is taking place, or the momentum is going out, causes the reaction force, which is the thrust. Now, since the flow is supersonic, the exit pressure at the nozzle does not necessary to be always equal to the ambient pressure. So, it is not necessary that P will always be equal to Pa, that we already learned from our previous courses like high speed aerodynamics or gas dynamics course, where we have seen that P may not be equal to Pa. In a case of where P is less than Pa, we consider this case as over expanded nozzle. So, of course, this will have some issue with flow separation, and since it is not the optimum expansion, your performance will decrease, it will decrease the performance. In an ideal case, what you want, we wish that P is equal to Pa, that is the optimum expansion, and in all our ideal rocket assumptions, we said that the gases exiting the nozzle is optimally expanded, that means our exit pressure is equal to the ambient pressure. So, the influence of the flow separations, decrease in performance will be even considerably low or can be neglected. So, that is the ideal cases. In most of the following discussions, we generally consider the optimum expansion for the simplicity of the analysis, but we should actually know that what are the in real case when the P is not equal to P A. So, in case of P less than P A, which is like near to sea level cases where your exit pressure is less than equal to the ambient pressure. So, that case is called the over expanded nozzle. There will be issue with the flow separation. So, that will decrease the performance. In case of under expanded nozzle, so your rocket is flying higher and higher. So, at a higher altitude the ambient pressure decreases. So, in that case your PE will become greater than PA. So, in that case it will not expand properly. So, that case is called under expanded nozzle. So, of course, the expansion of gas is incomplete, and of course, the performance will decrease in this case as well. Anyway, so these two scenarios I think you are well aware of, because in the previous course, either in your elective course or in the basic courses, if you have taken the compressible flow, if you have taken the gas dynamics course or high speed aerodynamics course, you must have encountered this phenomena like over expanded nozzle, under expanded nozzle and the optimum expansion. So, the discussions underlying theories, I think since those were already discussed in those courses. So, the participant may revise these things from their notebooks or the reference textbook. So, we are actually keeping it aside from the particular course. Now, let us try to see what we can get from this thrust equation, how much simplification we can do, and we try to understand how the thrust coefficient is important in terms of the thrust data. So, if you recall, we had the equation of the Vj we had derived in one of the lectures. We already got the equation of Vj as square root of 2 gamma universal gas constant into chamber temperature Tc gamma minus 1 into molecular weight into 1 minus P by Pc to the power gamma minus 1 by gamma. So, that was the equation for Vj or the efflux velocity. We can write this Ru by m dot equal to simply R, because that will save some space in writing the equation. So, we can simply say R Tc by gamma minus 1, and it will have like 1 minus P by Pc to the power gamma minus 1 by gamma. Now, let us recall the equation for m dot. We had the relation of m dot with respect to the chamber pressure, throat area and the characteristic velocity by this equation, like m dot equal to P c A t by c star. Now, if you put the value of c star here, we can write P c A t divided by the equation for c star was R T c by capital gamma, which is going to be equal to P c A t by R T c divided by square root of gamma into 2 by gamma plus 1 to the power gamma plus 1 by 2 into gamma minus 1. I think we should remember these equations all the time, because in many occasions we have to recall the equation for C star and the Vj. So, it is these are very important equations. So, we should remember these. Now, if you come back to the thrust equation, we can replace the Vj and C star by the previous relations we got. For Vj we got this one, and for m dot we got this one. So, we can replace m dot and Vj in our thrust equation. So, let us call this equation as 1, this one we can call it as 2, we can call it 3. So, let us use the relation of Vj and m dot, which is like 2 and 3 into equation 1, and we can write F equal to PCAT by RTC into 2 by gamma plus 1 to the power gamma plus 1 by 2 into gamma minus 1. Under the square root we can write 2 into gamma RTC by gamma minus 1 into 1 minus P by Pc to the power gamma minus 1 by gamma, plus we had the pressure thrust, which is P minus Pa into Ae. Okay. So, we can simplify it further. We can write this in the form like this, F equal to, let us take out the Pc and At outside. So, Pc and At, it is just like a form of a force, because you see Pc is the pressure, At is the area. So, it is a multiplication of chamber pressure and throat area. So, eventually it is becoming a force. So, let us put other things inside, or maybe we can do it little later. First let us try to simplify this one, because there are so many gamma r inside the square root here and here also. Let us do some simplification and then we will do the next thing. So, we will write in this form into 1 minus P by Pc to the power gamma minus 1 by gamma. So, this is under the square root plus the pressure thrust as it is. Now, let us try to keep the PCAT outside and all others inside this second bracket or the curly bracket. So, we can write 2 gamma square by gamma minus 1 into 2 by gamma plus 1 to the power gamma plus 1 by gamma minus 1 into 1 minus P by Pc to the power gamma minus 1 by gamma, plus since we have taken PCAT outside. So, you have to include those terms here as well. So, you can write this as P by Pc minus Pa by Pc into Ae by At, bracket close. So, Ae by At is nothing but the area ratio, sometimes it is denoted as epsilon, if you recall, which is the ratio of exit area by the throat area. So, this terminology, which is inside the second bracket or the curly bracket, is known as the thrust coefficient. It is called thrust coefficient or Cf, denoted as Cf. So, eventually this thrust equation will become Pc into At into Cf. So, this is another important equation in terms of rocket performance, which we can use time to time while calculating the thrust. So, typically the values of Cf is varies from around, so Cf ranges from 0.8 to 1.9. Now, if we see the how to determine the value of Cf, we can write Cf in terms of thrust by Pc into At. What we can see here is that experimentally, if we are able to measure the thrust, the chamber pressure, throat area, we should be able to determine the value of Cf. Now, if you look at carefully about this equation, what exactly it is doing, the thrust coefficient is as if like doing some amplification to this force part, because PCAT is the force, PC into AT, pressure into area, which is kind of a force part. So, the thrust coefficient can be considered as the amplification of thrust due to the gas expanding in the supersonic nozzle as compared to the thrust generated by the chamber pressure if it is acting over just on the throat. Let me say it again. So, it is just like an amplification to the force generated by the chamber pressure over the throat only. If you look at only this part, it is like as if your chamber pressure is acting over the throat, that is the generating force, which is PCAT. So, if that is the thrust which was generated by the chamber pressure if acting over the throat, which is PCAT, that is amplifying by this parameter called CF. So, that is why the thrust is amplified by this parameter. So, this parameter, that is why it is called kind of an amplification factor. Now, to understand the effect of chamber pressure, the altitude variation in a nozzle configuration, or to correct the sea level results for flight altitude condition, it is very important that we consider this CF. It is convenient to use this thrust coefficient parameter. Now, of course, the maximum value of thrust will be obtained for the optimum expansion, as we already told earlier, which is going to be like P equal to P A. In that case, the optimum thrust coefficient can be defined as, we can write the optimum thrust coefficient denoted as CF0, which is for optimum expansion. That means, our PA equal to P equal to PA, optimum expansion case. So, we can modify the equation and we can get CF0 equal to the square root 2 gamma 2 by gamma plus 1 to the power gamma plus 1 by 2 into gamma minus 1 into 1 by square root of gamma minus 1 square root 1 minus P by P c to the power gamma minus 1 by gamma. So, this is the modified equation for CF, which is CF0 or the optimum thrust coefficient. So, we can easily write down this equation from the previous one, and we can take out this term, because P equal to P A. So, this will be neglected. So, we will simply have this one. So, from there we got the thrust coefficient CF0. Now, if you look at this plot, this is a plot showing the variation of CF0 or the optimum thrust coefficient with respect to the ratio of chamber pressure by exit pressure, P c by P. It has been taken from G.B. Sutton and Bibler's book on rocket propulsion element. So, this is one of our textbook used in this course. One can easily see it in the book as well. So, it is showing the optimum thrust coefficient as a function of pressure ratio, nozzle area ratio, specific heat ratio for optimum expansion conditions. So, you can see that epsilon are nothing but the area ratio, nozzle area ratio A by AT. So, for different nozzle area ratio, it has been given for different pressure ratio P c by P. So, as you can see, once the pressure ratio is increasing, the thrust coefficient is actually increasing, and for various value of gamma it has been given also. For for low value of gamma, it is going to be the higher value of CF0, whereas as the gamma value increases, it is actually dropping down. So, this is another important consideration. One can actually do this calculation by taking out the effect of gamma separately, effect of P c by P separately, just to understand how they are influencing on the value of CF0, because this is a kind of an amplification factor in the thrust equation. Now, after getting all these relations, we can try to combine some of these equations together in order to have some convenience in calculations. We can just look at what we have done here and in the previous lectures, we can combining the performance parameters. See, what we understood in the discussions or even in previous courses, that the thrust developed by a given propellant would depend on how much high temperature gas is generated in the combustion chamber and thereby increasing the pressure, and how low molecular weight of the product gas is being formed. Because if you recall the equation of Vj, we have said that it is going to be proportional to 1 by square root of molecular weight of the gas, whereas it is proportional to the square root of chamber temperature. So, basically if we look at the propellant side, if the propellant has the capacity to produce high temperature gas and thereby producing generating the pressurizing the combustion chamber, this will give the high performance. From the molecular mass side or the molecular weight side, we are expecting that if the molecular weight of the product gases are in the lower side, that will actually enhance the performance, because Vj is proportional to 1 by square root of molecular weight. And also there are other things in terms of nozzle performance. We had said the capacity to expand the gases in the nozzle, if it matches with the exit pressure, if it matches, the exit pressure is matches with the ambient pressure, we call it as an optimum expansion, and that gives us a better performance in terms of thrust. So, combining all the performance parameters we have learned so far, if we just start writing it, what we can write? We can write C star equal to P C A T by m dot, that we have already just seen in earlier class, and today also we wrote. We had written F equal to the amplification factor C f into P C into A T. We had already said the specific impulse ISP is going to be equal to F by m dot. So, combining this, we can write that ISP is going to be equal to, you can see this is kind of C star into C f. So, what we can say is that this specific impulse is kind of a composite index, which is relating the capacity of the propellant and the capacity of the nozzle, or the I would say the expansion capability of the nozzle, because C star is very much dependent on the propellant combinations or type of propellants which has the capability to produce high temperature gas. So, that is why the ISP, which is a multiplication of C star into C f, is a composite index of performance, which relating the capacity of the propellant to generate high pressure gas, and it also relates the expansion of the gas of the gases, I would say gases, because since it is a combustion products, it is a mixture of gases. So, the expansion of gases in the nozzle. That is why it is kind of a composite index of performance. And of course, the ISP will vary with P C and P. One can actually generate some performance parameter plot by keeping some of the parameters constant and just varying the others, and generate the how the ISP is actually varying with the P C by P by considering the ISP equation and keeping some of the parameters constant. One can generate some parametric study, the parametric plots. Now, looking at further at P A equal to 0, which is like a vacuum condition, we can actually write the thrust equation as m dot V j plus P into A. So, from there you can write the equation for ISP vacuum is going to be equal to V j plus P A by m dot, which is going to be equal to V j plus P by A t into P by P c into C star. So, we actually are combining the other parameters into this equation. So, of course, you can understand that ISP vac is higher than the ISP sea level, because at ISP sea level or the where P equal to was PA. So, which has like ISP sea level, we said it was equal to like V j, where we had P equal to PA. But in case of vacuum, it is P is going to be equal to 0. So, we can have the ISP vac as this equation. Okay. So, some of these relations, if we combining them together, it will be easier for us to understand, and also if we do some numerical problems, this will be very easier to recall some of these equations. Okay. So, next what I am going to do is I will try to bring some example problems and just to show how we can use the relationship to understand the performance of a rocket. Okay. So, I will just solve 1-2 example problems in the next class. All right. Thank you.